Okay, good morning. So I'm going to give you your exams a little bit later. Alright, I've already assignment on this chapter, and I'm going to go over some stuff. So we did go over part of this last time. Find a state machine. So if you have to describe find a state machine, what would you say based on what you have learned so far?
The choice of possibilities.
What's that?
The choice of possibilities
Choice of possibilities of what?
of like the different states. A certain, like the example that you gave, like the elevators have different levels. You can be on the first, you can be on the fifth level, but you can only go down to four. Where you can.
So there are set of states. So elevator has set of states. Each floor is a different state. To get there, it has some requirements, right? So that's what find a state machine is. So, well, we can start with something like this, and then you can think about it, and then move forward. So let's say we want to have we have a find a state machine. It takes X as an input. It outputs F. It has clock, reset, things like that. And let's say that it is recognizing sequence 001 from right to left, which means that if you get something like 001, 01, whatever, it's going to ignore those. It's going to recognize this as the first. It's going to recognize the second one and the third one. So when it sees 101, it's going to set F equal to 1. And then it can continue. And there's another one right here. And there could be another one right there. See if you can, I can do one example if you like first. If that helps. Or based on the elevator, would you be able to do this? So you can wait for a minute and then start maybe. So the way that these things work is that every time it recognizes like an elevator, a particular sequence, part of the sequence, the only way you can remember this, just like the elevator flow, to make it transition to a different state. Okay? When it makes it transition to a different state, that's how it remembers it. Okay, just like the floor in the elevator. I think we went through this, that once you have the state, you have to figure out what the next state is and what the output is. And here we have an example. I can show you this first before we can handle this one. So let's say we are doing a sequence of 101. You can see that it is similar thing, except that this one, the one on the screen, it recognizes 101. Okay. Every time it says 101, it needs to recognize it. So the way we do that is we say, okay, the arrow is, this is the first state we're going to start with. So let's say A. Okay. And then you can say, okay, what if I get a whole bunch of zeros first? Is that part of the sequence? No. So it's going to ignore that. Okay. So let's say X equal to 0, it's going to ignore that. As soon as it gets a 1, it makes a transition to a different state. Okay? Different state. And we have really two different types of machines. Okay. One is the outputs are on the arc, on the states. So let's say we can say the output is what do I call F. This is not that one, okay? Let's not get confused. 0, F equal to 0. And then what if we get So you have to think about all these different things. What if I get 0, 0, and then 1, 1?
You go back to A.
What do I do?
You go back.
But I could have
Oh, you
0,
can
1
stay.
after that.
You can stay at B.
Stay in B. Correct. So you stay in B. X equal to 1. You can have as many as 1s you want, and then as long as there's 1, we can, and then again we get a 0. It's part of the sequence, so we have part of the sequence, so we make another transition. C, still f is equal to 0. Okay, so let me draw f here so that we don't get confused with that one. This is also f. Then clock and reset. Okay. So okay, so we get a 0 here. X equal to 0, we're gonna go here. So what if I get another 0?
You go back to A.
There's nothing that's similar to what we want. So we have to go back to A. Start all over again. So what if we have 0 and then 1? That is the sequence, right? That's the sequence we're looking for. So we can go to D, set f equal to 1. This is x equal to 1. So 1, 0, 1, we should recognize it. Yes.
Over there on the B, why you just directly go, not going back to A, since you get 0, right?
But that is part of the sequence. See, we are looking at 1, 0, 1. So 1, every time you see part of the sequence, you want to make a transition to different state. So you're trying to remember what you have received. And the way you can remember it is by being in a different state. If you're in C, that means you have received 1 and then 0. It could be 1, 1, 1, but you have received this portion of it. You have received this portion of it. So you always make transitions, and that's how you remember. And then if you get 1, 0, 1, that is all of it. So we should recognize it when we set the equal. Okay, so here we could get. What if we get a 0, another 0?
You can go back to C.
We need to go back where we ended up at 1, 0. So we go back here. X equal to 0, because we could get, if it says overlapping, let's assume overlapping. Overlapping, okay? So overlapping, this is overlapping. Sometimes it's not overlapping. And then, so we can get another one, and that would be another sequence. What if I get a 1 after that?
You go back to B.
Go back to B, because I could have 0 after that. X equal to 1. So we have one X, we have one input, we should have 2 arcs leaving each state. That's a quick check. 2 is leaving, 2 is leaving, this one, 2 is leaving, 2 is leaving. So that's what, so once we complete this thing, then we can translate it into circuit. We can translate it to circuit, and it will work. So why don't you try this one? This is called, it's just strange, but
You want us to do overlapping with that one?
that one, I don't think overlapping is going to work. This is called Moore machine. I mean, it's kind of weird. Somebody's name, but it has more states than the Mealy machine. We'll talk about Mealy. Yeah. So try that. It won't be overlapping because we only are looking at 3 bits. So try that while I'm taking attendance. Ahmed? Lawrence, John Lawrence? Joshua? Here. Benjamin Chisholm? Tori, last name. Julio? Alex? Giovanni? Maxwell? Cameron? Henry Hill? Gwen Pope? Alisa? Jagjit? Julie? Jonathan Lee?
Here.
Leon? Steve Lord?
Here.
Dan? Mangati? Alex? William Harris? Nicole? David Nam?
Here.
Reese Nelson?
Here.
Hadad?
Here.
Jeremy Painter? Nicholas? Mark? Van Gunpowel? Dennis? Pablo? Sukraj? Samir?
Here.
Shams? Here. Singh? Sarab? Sarabchat? Timothy? Timothy? Handel? Here. Here. Kevin? Here. Brandon? William? Here. What's your name?
Cameron. Cameron is something.
Evan?
Oh no, Cameron.
Cameron?
Yes.
What's your last name?
Saudi, HESSA.
What's your name?
Timothy. Timothy.
Last name?
Talapis.
Okay, somebody get this?
I think you missed me.
What's your name?
Ezekiel, Liam,
Last name is Leo.
Liam, Leom.
Anybody? Yeah, why don't you come and try? Why not? But when you recognize you should generate it.
Oh, I see where. Oh.
So you got the one, yeah, you get the one, zero, zero, you recognize. Then if you get a zero, then go here, and one, here, and one, bring it down. Looks correct, seems. So normally for this, we put the function values down below. This is fine, but leave it down below. Okay, so this is the hardest part of designing sequential circuits. Meaning sequential circuits that it's not easy to tell what is the combination circuit that's going to generate this. We only use this for smaller circuits, things like this. Something that is not easy to figure out what the solution would be. Okay, so later on, this is only for smaller problems. Later on, we will, like CPU is a sequential circuit, but we don't design it this way. CPU has 60 hundreds of instructions. We don't design it this way. This is only for smaller problems where you can't tell. We'll do it with examples of both. So this is one example of this we can, and then we do examples that using existing modules. Okay. So this is one type of machine that we design. Uh, this is called board machine, which means the
Are they usually in squares like that, or is it okay to have it linear?
yeah, it's okay. Doesn't matter. It's just that if you have linear, you're gonna have a huge, sometimes huge.
Einstein, yeah.
Does everybody have a hard time with Windows 11? It's kind of weird. Right now I was showing presentation there, but it wasn't a presentation for here.
It seems to have a lot of driver issues.
Lots of
I've got one where it thinks my trackball's always connected, so the trackpad gets messed up.
I updated mine last night, but still is. Okay, so this is 101 that we did. So from here, we go to pointers. From here, we know how to. See, this is. Let me just go back to this for a minute. This is the overall design. This is what the final solution should look like. A whole bunch of flip-flops. There should be a circuit tells you the next state. But if you're here, if you get X equal to 1, you have to go to the next state. So there's a circuit that's going to tell you where to go. And we will assign, we will also need to assign binary numbers for these states. So if we have 4, we could say this is 0, 0, this is 0, 1, 1, 0, 1, 1. Those will be the state numbers. If you assign it differently, you get a different circuit. So this circuit, as the name implies, next state generator, or NSG for short. Okay, it's gonna the Q's. So the Q's, these are going to be flip-flops. I mean, sometimes we can use 4 flip-flops, but that's only special cases. Here, how many flip-flops do we need to have these bits? 2, right? So the Q's is going to be where we are. Q is the content of the flip-flop, and D is the next state generator. So Q goes in here. They may have inputs, like in this case, X is the input. It will tell us where we need to go. And this one is the output generator. The only place that we're generating output is when, where are you generating F equal to 1 over here? F equal to 1. So this is going to generate the output telling us the F. So all of them is going to look like this. There are 2 different types of machines, the Moore machine and the Mealy machine. And the difference is really this arc. Moore does not, the output does not depend on the external output. So every time we get to this point, this is a Moore machine, you're going to generate F equal to 1. It doesn't matter how you done it. We'll do an example of Mealy. Some problems, Moore is easier, some problems, Mealy is easier. That's why we have 2 versions. Okay, so now that we have a finite state machine, we're gonna try to design it the way that's shown. So for this one, how many flip-flops do you need? So how many bits did you use to label these states? 2 bits. So 2 flip-flops. Okay. And the input is X, and output is, in this case, we call it Z. Okay. So the block diagram of design is going to look like this. We have 2 flip-flops. Q's are Q0, Q1. This is the next state generator, D0, D1. It has a clock. We reset the system. And then there's only one input. So given the current state, which this is going to indicate, and X is going to tell us where we're going to go next. And then these 2 is going to tell us, this is a Moore machine, so it's going to tell us that whenever we get to state 1, 1 on the diagram, it's going to give us the Z equal to 1, just like F is equal to 1. So we call it C in this diagram. Okay. Mealy, on the other hand, we'll see an example that really the output is going to depend on X. This one, the Moore machine does not depend on X. As I said, some problems are easier to design with Moore, some problems are easier to design with medium. And it's less uses fewer flip-flops. Okay. So basically, it turns into a combinational circuit design. What do we do in the combinational circuit design? How do we design combinational circuit? What is the first thing we do?
State table. I mean, truth table.
Truth table. The first thing we do is a truth table. So that's the combinational circuit. So what is the truth table for that? What are the labels? I mean, by this time, only one student shouldn't tell. Everybody should say truth table. Combinational circuit is truth table. Okay. So we can determine what the inputs are for the next state generated. Okay. So that's the block diagram. So what are the states? Let's see what order I have. Okay. So it has Q1 and Q0. So let me just draw it over here so we know. So this is the output generator. This is the next state generator. These are the flip-flops. For clarity, I mean, we can, sometimes you put the D on that side, but it's better just that we are using usually inputs from the left, outputs from the right, or from the bottom. So we are flipping the flip-flops over here. Okay, so these are the flip-flops. So we can label it Q0, Q1. I have labeled it. Yeah. So it matches the notes. And then this is P1. So these bits are telling you the next state. And then we have a clock, reset. Okay. Resets are connected together to a switch. And then the clocks are connected together to a clock. So this is going to tell us where we are. And based on the X value, where we're going to go next, on the next clock, Q is going to become D, right? That's what it is. Q becomes D, so we transition to the next state. So this, present state. This becomes the present state. Present state. Where we are now, given the X, where we're going to go next. This is going to tell us where we're going to go. When the clock comes on the rising edge or the falling edge, it doesn't matter, one of them, then the Q becomes D, we make a transition to the present state. That is how we make the transition from here to here when the Q's are changed based on the D values. And then they go in. So they go both in here. This is a Moore machine, so it doesn't have any inputs coming in here. Medium machine, this input will go here as well. So the output in this case depends only on the states. Only on the state. It doesn't depend on the axis. Immediately you'll see that outputs will be on the arcs, not on the states. So that means given the state, given the x, you know what the outputs are. So this is what we are trying to do. So you can create two truth tables. So output is input is also, this one also has an x value. I'm going to put it in the right order. And then we have D1 and D0. So that's going to be one table. There will be another table that we do. Here. There'll be another table between Q1, Q0, and this would be the C output. Okay. So in this case, it's not part of X is not part of that because it's a Moore machine. Okay, so now we have already assigned state numbers. So on reset, we're going to go to 0, 0. And then, okay, what is X? If X equal to 0, so So this is the initial. This is the different. This is the different problem, right? This is the different problem.
Yeah, this is 001.
Yeah.
think the
I
other
can
one
bring
we
this.
have is one
I can
zero.
do this thing. This is the one we are doing. This is the final state diagram here. So if it is 0, 0, we're going to state in 0, 0. If it is 0, 0, 1, so let me erase this so there's no confusion. This was the example that we did in class. So you can see from there when it is 0, 0, so state A, say state A, clarity 0, 0, 1, we're going to go to B. So that is state 1. So this is state A, state B. Okay. And then we are in state 1. State 1 is state B. I don't know, should I just put that on the board? Is that, can you relate to that? Or should I put it on the board?
Every state has an input and an output, and the two outputs of what it can be and where we're going, right?
Every state has one in X.
But it can go to two different, if it's an X
Yeah, of
one or
course.
X zero, there's
Yeah.
two different ways.
Different ways. For every different value, you have a one option. In this case, A is we have assigned 0, 0. State B, we could have 0. So if you're in state B, if it is 0, what do we do? State B, what do we do?
Go to state C for zero.
Okay, we go to state C, which is 1, 0. Is everybody following it, or just one person saying it? Or everybody can say that. Okay, so what if we are in state B and we get a 1?
State B.
State B.
So state B, so that's going to be state B. Okay, now we go to state C. So if it's 0, what do we do?
You go back to A.
State C, we go back to A.
Yeah, that's for
One
C.
alone.
Oh yeah, okay. So 0, 0, go back to A. If it is 1, we go to D. Right? Go to D, right?
Yeah.
Okay. So that is 1, 1. Okay, now we are in D. If you get a 0, go back to
Go to
C.
C.
You go back to C. And then if it is 1, 1, 1, what do we do? You go back to B. Okay. Can you, right now, these are the outputs. These are the inputs. Okay. And what are we designing right now? Combinational circuit. So can you get equations for D1 and D0? What do we need to do? This is right after the exam, right? I mean,
Some products, or product of some.
yeah, sum of product. Just sum of product. So for that you do what? K-map. So go ahead and do K-map and tell me what the equations for D1 and D0. Your second exam is going to have one of these problems. Anybody has a solution? Anybody? Yeah.
So zero equals X.
Or do you want to dot Q1 X
Q1, Q0
Q0
X.
X plus Q0 X?
Okay. What about Z? I don't know. Let's see everybody in the same thing. 0, 0, 1, 0, 1, 1. The only time that Z is equal to 1 when we are um, in state D. Again, this is state A, B, C, D. So Z will be Q1, Q0. Did everybody get those D0, D1, those equations? Okay. So we were here, we had the flip-flops, we created truth tables for those from the state diagram. These are the truth tables. Then we do the minimization. Voila, we've got the circuit. So these are the Q's. This part is the next state generator, generates D1 and D0, and this one, which is Z equal to Q1, Q0, is the output. Okay, so this is, in reality, this is how it would be implemented. They don't put all the flip-flops on the chip, one corner, and all the combinations come out. It's all embedded. So this is how it would be generated, designed, implemented. Okay, straightforward, right? So minus the diagram, the way that exam questions are would be two parts. One would be draw a state diagram for a problem. The second one would be like given a state diagram, it would be circuit. Okay. So what if you change? We labeled the state diagram as 0, 0, 0 for A, 0, 1 for B, 0, 1, 0 for C, 1, 1 for D. If you change them, it won't be incorrect. It's just that the circuit will look different. You see, this is a slightly different assignment. You see, we've switched a little bit. There's some kind of an algorithm also that decides what these are, but we just chose in a simple way to do that. So you can get a different equations depending on how they are labeled. And yet there's another design that they use in field programmable gate arrays, FPGAs, field programmable gate arrays. Those are prefabricated chips that they're programmed. You can program than any hardware. And they have cells, and every cell has a flip-flop. So you got unlimited flip-flop. If you have 1,000 cells, you have 1,000 flip-flops. So it's not limited. So in those design, in those cases, we try to use more flip-flops because it simplifies the combinational circuits. Okay, but those are only applicable in field programmable gate arrays. Okay, and design details are a little bit different, but truth tables are a little bigger and so on. Okay, the next one is a different one, is the Mealy machine. The Mealy machine, you can see that the outputs are on the arc, not on the states. So for the same problem, it's going to use fewer states. I mean, in this case, still we're going to use 3 flip-flops, but in general, this problem, this kind of design requires fewer flip-flops. Okay, and it's easier for some problem. Mealy is easier. For some other problem, more is easier. Okay, so this is going to be that. You can. I want to have time to give the exams back. So take a look at these. We covered that on Thursday. Uh, similar type of design. If you want to read ahead, what if we have unknown states? Okay, so we have 0, 0, 0, 1, 1, 1. But what happens if it goes, due to surcharge and different things? What if the system goes to 1, 1? Then what do you do? There are different solutions for that. Fault tolerant is another solution for it. Okay, so we're going to cover that. There's not much I mean, there's a lot in chapter 5, but I'm condensing it to the major things so we have time to cover other chapters. So review, take a look at the next. I have assignment for chapter 5. So you can take a look at those. We should be able to finish chapter 5 next on Thursday, and maybe even start chapter 6. Leon?